some of this talk is work that I've done in collaboration with Michael Silverstein and Robert Bishop. So we're currently working on a book called Contextual Emergence. We're trying to develop that. But just for you guys, I've tried to give it a unificatory spin to make it a little bit more interesting. So I'm going to make three basic claims in this talk. One is that emergent phenomena are inherently contextual. That means that the necessary and sufficient conditions for specifying the system don't come from things internal to the system themselves. They come from a confluence of things internal to the system and things outside the system. Now, often these background conditions are things that we ignore because they're so familiar and they're not the primary focus of our investigation. But that doesn't mean that they're not very important for the actual manifestation of properties in the system. The second claim I'm going to make is quite a controversial one, and that is that causation itself is an emergent property. So that the causal relation itself is something that is emergent in a contextually emergent way. And the third is, which is the most speculative part of this talk, which is that this might have some application to kind of unificatory schemes. I'm trying to address the question of, does unification itself lend towards a kind of reductionist viewpoint, or is it compatible with an emergentist viewpoint, and is there a way that contextuality can say something different about what's going on in a unification? Right. So,
can I hit the light behind you?
Sure.
To make it easier to see the screen.
So, I'm sure all of you guys are familiar with these kind of emergence reduction kind of debates, but there are kind of different things in play when we talk about emergence versus reduction. First is relationships between explanations and theories. So that's whether one theory reduces to another. So does thermodynamics reduce to statistical mechanics? Does classical mechanics reduce to quantum mechanics? The second is the relation between the physical and the mental. So for philosophers' mind, what really matters is this distinction between these two things in the world, mental properties and physical properties, and can you cash out mental properties as being nothing but physical properties? So I'm not really going to talk about either of those first two, really. I'll touch on the first one. I won't mention the second one at all. The third one is what I'm mainly going to be talking about, which is the relationship between aggregates and the particles that make up those aggregates. So it's the system and its properties versus when you take those particles and put them in an aggregate, what properties they have. So here's an example of all these little particles, and they're interacting in certain ways, and you might have some global properties, and the question is, where do those global properties come from? Are they purely resultant from the particles, or is there something genuinely emergentist about it? So, again, disclaimer. Here's a game of life. I love these things. So, the game of life, if people aren't familiar, is a little game you can play with a piece of graph paper. It's even more fun on graph paper. Get your graph paper, get your marker, and have a set of initial conditions and a set of rules for colouring in the little squares on the graph paper. And before long, you get all kinds of interesting patterns which sort of recreate things that look like they're alive. Hence the name game of life. Right. So in this case, we know all the initial conditions, and we know every single law that applies to the universe, and we get patterns that come out of it, which we couldn't have predicted in advance. But the patterns are causally inert. They don't do anything. They're just patterns in what's going on. Right? So I'm going to argue the world is not like this. Right? But in the emergence literature, you'll get terms like strong and weak, and I think they're kind of unhelpful at best in the emergence debate. Because whether this counts as strong or weak emergence depends on kind of how people are subjectively using those terms. There's no well-defined set of uses of those terms in the literature. And they don't really get to the heart of what's different. If I say that something's weak emergence or strong emergence, whether you think that's significant or not depends on your prior intuitions about what those terms mean. They don't identify different categories in the world. What really matters, I think, is the distinction between epistemic and ontological emergence. So epistemic emergence would be the idea that we as observers could have things in the world, properties which are novel or emergent, which are irreducible in some way, but they're simply like the patterns in game of life. They're patterns in how we perceive the world. But if we were to take a kind of Archimedean view and see the world as it truly is at the fundamental level, with infinite computational or representational power, we wouldn't need those patterns. They don't do anything in the world. They're not part of the true ontology of the world. You get all of them for free just by specifying the initial conditions and the fundamental level. So the second claim is that there's ontological emergence, which is there is stuff in the world, there are things, properties, entities, structures that don't reduce, that are irreducible, that are in the world just as fundamentally, I would argue, as what we dub the fundamental level. So, now, although these are two distinct categories, they do overlap because often the epistemic failure of reduction is used as evidence for ontological reduction. So it's kind of like a smoking gun. You go, well, if our theories and explanations and kind of our perceptual states don't reduce, maybe that's telling us that the actual matter in the world doesn't reduce. So the former potentially provides evidence for the latter. Now, I'm going to kind of assume that as well, but it's just an aside. I want to make the point that that's a very naive assumption that the epistemic argument informs the ontological argument. And it relies on things that often go unacknowledged amongst kind of philosophers of science, things like an implicit belief in what's called the explanatory indispensability argument. So that argument goes something like this. If I have an explanation for the world, and there's a term in that explanation which I can't remove from that explanation, then that term must be something in the world. So if I have to mention electrons to explain how atoms behave, then electrons must be a real thing in the world, you would think. It's not true, or at least it's very controversial. It's not obviously true. So there are examples. Alyssa Boklich argues, for instance, that you can have what's called fictional explanation, which is you have explanations of phenomena that cite terms that we know do not exist, yet they are indispensable for the explanation. And not indispensable in the way that a piece of mathematics might be. They're indispensable in the story about what's happening in that system. Right. So this is, I won't get into this too much. This is an example called wave function scarring. So it's a quantum chaotic system, which is a bit of a misnomer. There's no such thing as a quantum chaotic system. But it's a quantum system that replicates a pseudo-chaotic system. And in that, what you would expect is, because it's a quantum system, if you hit a quantum billiard ball around a table, you'd expect an even superposition of all states. But you don't see that. Instead, what you see is here, when you have these kind of, they're quite difficult to see, but definite patterns of pathways around the quantum billiard that correspond to what the classical stable orbits would have been in the chaotic system. So it's a purely quantum system with no classical states, but yet somehow the quantum system, if you were to explain it fully, you could explain it computationally, you could just do the raw numbers, but if you could actually explain it, you'd have to make reference to non-existent classical pathways. So, the only point I'm making is epistemology isn't necessarily always a good guide to ontology. I'm also going to say that I think to have a robust emergence debate, you have to kind of presume some kind of scientific realist stance. So, for an anti-realist, scientific theories don't tell you what's in the world anyway. So it doesn't really make much sense to have a big argument about whether science is telling us, for instance, that table doesn't exist and instead it's made of atoms, if you're an anti-realist and you don't think atoms are a thing in the world, or that science gives us warrant to think they're a thing in the world. So, you kind of have to be a scientific realist. Right. So, question, contextuality. Right. Well, I think an obvious thing is that human language is highly contextual. If you shout fire, it really depends on what's happening. If you're on fire, that means one thing. If you're not in fire and you're in a crowded room and people stampede and there was no fire, it means something entirely different. Human language is inherently contextual. We all intuitively know this. And the reason for this is pretty obvious. It's because humans occupy a phenomenological world which is a combination of the world of objects and the world of meaning that those objects have. So the same physical object could have two entirely different meanings at different times, at different spaces. You can imagine a widow going back to their kind of house where their husbands died, and it's kind of the physical object is the same, but the meaning of everything in that place is different. Human beings occupy an inherently contextual phenomenological space. But what about the world? Well, I'm going to try and define context. It's a little bit difficult because it is a kind of broad term, but I'm going to try and be as specific as I can about it. So context is a set of environmental circumstances outside the domain of the system in question. Right? So it encompasses, but is not limited to, things like stability conditions, the things that have to exist outside the system to allow the system to be stable enough to persist in time and have properties in the first place. Boundary conditions, system environment boundaries, which I think is a crucial part of contextuality, which even among contextualists isn't talked about much. It's not just the things outside the system, it's the actual demarcation of what is the system and what's outside the system that itself has importance. So these contexts provide a set of constraints together with what's happening in the system. And the constraints close off or open up sections of modal space, possibility space. What has to happen, what can't happen, what might happen. The constraints are contextual because they're produced by the particular confluence of circumstance, the system and the environment that it's in. The system on its own doesn't have that set of constraints. The environment alone doesn't have those constraints. It's only the confluence of the two. Right. What's the nature of the constraint? Well, this is ongoing work to try and tease out different senses of constraint in the model space. Are we constraining it logically, metaphysically, physically, nomologically? I'm going to hedge my bets and say it's about physical and metaphysical constraint at the moment, but I'm kind of open-minded about in what way contextuality constrains systems in these different hierarchies of constraint. Just as a complete aside, although it will come up later on hopefully, there are generally two competing ideas about the nature of constraint anyway. If we take something like physical constraint or nomological constraint. One is what I would call this kind of Russian doll idea, which is that whatever's at the fundamental level constrains what's above it, and that set constrains what's above that, and so on. So fundamental physics constrains condensed matter physics might constrain chemistry constrains biology, and so on. Biology constrains sociology, that is, something can't happen in the chemical world which is impossible in the physics world. Right? Now, each model space is a kind of proper subset of the one below. Now, I think this is true, but like Bohr said about truth, the opposite to a truth is not a lie, it's another truth, it's a contextual truth. And I think, although this is true, it misses an important aspect of how model spaces operate, which is that they're much more interconnected. So instead of having separate sets of model space, where one just sits passively inside the other, instead they're more like a honeycomb of connected model regions. And the model regions can only be reached by sometimes passing through a higher model space. So let's say we've got an area of physics here, and we want to get to another area of the model space of physics. Now, this pathway might actually be blocked, and instead we have to go up to some other zone to then reach. So the idea is that instead of this model space just being a subset of that model space, it's obviously constrained by it. There can't be things happening here that are impossible here. But it's not passive. It's not irrelevant to this. And that's the common idea about model spaces, which is, if I'm a fundamental physicist, why do I care about the model space of biology? It's got nothing to tell me about physics. Right? So, I think this is pretty straightforward to see examples of this. Where do the heavy elements come from? Well, they don't come from the Big Bang. We only get up to lithium. So where do they come from? They come through astrophysical possibility space. You have fundamental physics, let's say the standard model, and pretend that's fundamental. You've got the standard model. You've got all of those particles. But they don't produce iron. They don't produce uranium. You have to have a set of circumstances where those fundamental physical properties combine in a certain way that they enter a higher level model space, that of astrophysics, where what's possible in the model space of a star is how you get from A to B in the fundamental space of the particle physics. Another example might be if we wanted to clone a sheep. Well, clearly cloning a sheep is biologically possible, but the way it happened in our world was that we had to go through sociological space. We had to invent science, have human beings that could manipulate cells in certain ways to then clone a sheep. So I think all of these model spaces are deeply interconnected, and they can't necessarily be ignored that you're trying to exhaustively account for a phenomenon. So, contextuality, toy example. Let's imagine we've got a game of cricket. Right? I know nothing about cricket, so don't ask me cricket questions. Right? So, the properties and relations of the game itself. There's the cricket game. I don't know what that involves. Men with bats and balls, I don't know, something to do. Seagulls, apparently. So, there are cricket things. But then, there are a series of background conditions which, if I asked you to explain to a friend what a game of cricket is, you'd probably never mention because you'd just take them for granted. You need to have a physical space. You need to have a ground. You need to have a law of gravity. You need to have kind of, I don't know if you need grass or not, but you need things outside of the strict domain of the game itself to even manifest the game. They're stability conditions that allow the game to proceed. So if it rains, the game stops. So the game depends on the weather in a way that's completely not explicit if you're just to consider the properties and the rules of the game itself. Right? Now we've got an alien friend who, like me, thinks cricket's boring. So our alien friend comes down, and they've got a slightly different problem. It's not that what's background and what system is intuitive to them so that they don't notice it. It's that they have to do some hard work to decide the boundary of the system in question in the first place to actually specify its properties and relations. And it matters where they draw the boundary. So if our alien friend here looks at the game of cricket but thinks that the spectators are part of the game, when they account for the rules and properties of the game, they're going to get a very different set than if they correctly demarcate what's the game and what's external to the game. Right? Now, I'm going to argue that this system-environment distinction is not arbitrary or purely epistemic, but it is highly perspectival. So what I mean by that is, if we were to all go outside and stand around this building and look at it from different angles, we would each have a unique perspective on what's going on, but it wouldn't be arbitrary or just epistemic. We could each swap places, and if we were stood in the opposite person's place, we would have the same viewpoint. So there's an Archimedean view that gives you an overview of everything, but that doesn't mean it's arbitrary. So, once you've specified this distinction between system and environment, that is what allows you to describe a vocabulary of what I'll term atomic terms. So by that I mean things that are analogous to the way that 19th century physicists might have used atoms. They are whatever is the basic term in whatever vocabulary you're using to describe ridiculous systems. It doesn't mean actual atoms. It could be anything. So explanation for me is about mapping patterns of modal relations using those atomic terms. The atomic vocabulary is not the most fundamental vocabulary you could describe the system in terms of. Right? So someone like David Lewis would say, well, the thing that's fundamental is space-time relations, so we should describe everything in terms of space-time relations. Well, that's because David Lewis has never done a piece of physics in his life. It's like, the thing you do in physics is you look at a system and you go, what's the simplest vocabulary to describe the properties that I'm interested in that system? And what that vocabulary is highly contextual. Specifying the atomic vocabulary requires input from outside the system, whether you realise you've used it or not. So this is the kind of classic argument in a lot of kind of these debates about emergence, but also in other areas. If you look at David Deutsch's kind of interpretation of Everettian relative state quantum mechanics, the classic argument is that he recovers the probabilities because he kind of knows you should have them, he's kind of snuck them in without even realising it himself. And that's the classic argument against some reductionist critiques of emergence claims, where you go, yeah, but you're only able to reduce that because you already know what the macroscopic state should be and you're using information from that to construct a bridge. But that's very different from it only being information from the system itself. So, two versions of contextual emergence. One is just an epistemic claim. So the contextual nature of describing systems means that you have to use information from outside a system to reduce one system to another epistemically. Right? Ontological contextual emergence. This is what I'm most interested in. That the contextual manifestation of properties and modal relations is what the world is about. So every time there's a property manifestation, it is because it's this intersection between a system's properties and the context that system finds itself in. So, epistemic contextual emergence. As I said, context have to be used to construct a bridge principle to define observables that allow you to reduce one theory to another or one explanation to another. Right? The contextual features are not part of the reducing theory. They're things from outside it. You know, if we think about kind of trying to reduce classical mechanics to quantum mechanics, and we have some kind of boring correspondence principle, where does that even come from? It doesn't come from the fundamental theory. It comes from the top theory. We put it in by hand, and we might not acknowledge it because we call it a boundary condition, but it's still information relevant to that system. Right. Epistemic contextuality is necessary for the construction of explanations. Right. Without contextual epistemology, we couldn't partition systems into the variables that we need to accurately represent the possibility spaces. Right. So, laws, explanations, are summaries of model information. Laws give constraints. Without the modal constraints, you can't account for the system. So, for instance, if you're going to talk about something in condensed matter physics, it really matters often what the dimensionality of that system is. Now, the dimensionality is not properly thought of as part of the system. It can be in certain circumstances, but generally speaking, it's not. In an astrophysical explanation, if you're going to explain why it's possible to have stable planetary orbits. That crucially depends on the number of spatial dimensions that you have. That's not part of the planetary system. It's something that sits outside it. Right. Now, this is a crucial point as well. What's relevant to say is that atomic units are not merely choices that we make. They're the unique set of variables that allow us to do two things. Capture all the salient modal information, but not include irrelevant modal information. So it's really important to remember that about explanations, which is an explanation is not made better by including irrelevances, it's made worse. So what matters in an explanation is the precise set of modal information that you want to capture. If you have an explanation that includes more detail, more microphysical detail, say, and that includes irrelevances, you haven't improved the explanation, you've made it worse. So, I won't spend too long on this, but if you want to get kind of technical about this, you can talk about algebraic approaches to physics, and you can compare things like quantum field theories with statistical physics theories. Right? And in these theories, you can define what's called an algebra of observables. Right? And each one of those has a different what's called topology. Right? So a contextual topology is a mathematical space in a domain of physics that's been enriched so that it corresponds to the relevant algebra of observables in that target system. Right? The enrichment's carried out by incorporating information from the target domain and its context, not just the target domain. So one way of thinking about this is that if you were to create this kind of algebra of observables, what you'd need to do is to specify, say, the relevant symmetries in a condensed matter system. Now, those symmetries themselves don't just come from the system. They come from boundary conditions and constraints placed on the system. Right? So the contextual information is not given by what's called the finer topology of the lower level description. Right? So this is quite an old idea. This goes back to Primas, 1998. But it hasn't really been taken up in the philosophy literature until now. So I'll give a quick run through of how we do this. So you think about it in terms of set theory. You can partition a set up in many different ways. And each partition defines what's called a sense of nearness. So we take our set and our members of our set, and we go, these two things are related in some way and they're close to each other. But nearness isn't intrinsic. Right? The nearness is only specified when you specify a topological structure to the set. Right? So a topological structure, in a sense, picks out subsets of that set. Right. So here's an example. So a very simple set, A, B, C. Right. So we can structure that set differently. So we can draw a relation around A. Right. And then we've got kind of a different topology. This is now a different set from the first set. Or we can do more complicated things. We can have a relationship between A and B, or an intersection of A, B, and C. So we can do different structurings of the set. So each one of these terms might be a term in a theory that you're then relating to be able to account for modal relations in the world. Right. Not all topologies are allowed. So it's not purely arbitrary. So just like with the model space, the set theoretic description is constrained by whatever your fundamental set was. It doesn't allow any old topology to be said. Right. But it is multiply realisable with respect to many different topologies. We can also compare topologies. That's not always true. Sometimes you can't compare topologies. But if you can compare them, then you can say that we have a notion of fineness or coarseness about whether one topology is a proper subset of another topology. So, what I'm arguing is that each new topology is a different way of specifying a new context for a system. It's a different way of drawing a system environment boundary. It's a different way of shuttling off things into boundary conditions and constraints versus first-order parts of the system. Right? So this is a quote from Primas. So the important bit about this is that it says, neither domain is contained in the other. Although higher-level theories can be derived rigorously from a more fundamental theory, they are not sub-theories of the basic theory. Therefore, higher-level theories cannot be totally ordered, and theory reduction is not transitive. Right, so it's really important to understand what's going on here, which is like you can connect theories, but you do them through singular limits that you have to input contextual information into to recover. Right? So really, it's a question of if you want to think about it in emergence terms, it's a question of whether something is nothing but what's underneath, or it comes from the thing that's underneath, but it has some irreducible component to it. Right? So it doesn't mean it's disconnected or it's kind of novel in the sense of completely free floating from what's underneath. It's highly constrained by it. Right. So here's a summary of epistemic contextual emergence. Right. Atomic variables are almost never the microphysical variables. I'd argue they're never the microphysical variables because we don't actually have a fundamental theory, and we know we don't have a fundamental theory. So all of physics is based on non-fundamental terms. That's why I'd argue. Right. So we never use the microphysical variables to capture the model information. Because what the model information we want to capture is highly contextual and depends on what we're trying to explain. Right. Atomic variables are only definable and applicable if we use contextual information. They're necessary for expressing model facts. And reduction would require reducing atomic variables and contexts, which is the obvious move to go, well, why is this the emergentist? Can't you just say the system reduces to the low level and the context reduces to the low level? But it's really hard to argue that, I think, a priori, without doing some hard work to justify that assumption that you can always reduce a context. Because the contexts are so highly heterogeneous with respect to systems. So you might have some system, say for instance like the fractional quantum Hall effect, where you have things that you think reduce. So you go, well, I've got a collection of electrons in an aggregate and they're interacting. So that'll just reduce. But then it might depend crucially on something about the dimensionality of the space in which the system's embedded. It's not obvious that that reduces. Now you might counter by saying, yes, but something like dimensionality is itself a part of the fundamental structure of the world. We'll include that in the set of what we call the fundamental. It's not entirely clear that all contexts are going to be easily described as fundamental in that way. And if we think of a biological system, it's not obvious that everything that matters contextually to how a beehive works is obviously going to either be reducible or itself fundamental. So, ontological contextual emergence. This is a much more radical claim. Insofar as epistemic contextual emergence is a theory of emergence, I think even a lot of reductionists could be fairly happy with it in the sense of it's not arguing that there's a complete disconnection between descriptions in the world. It's only arguing that you have to import certain external information to facilitate reductions. And you could just argue that's just a more sophisticated form of understanding how reduction works. Ontological contextual emergence is a much stronger claim. So one claim is, what happens in a system, not how we describe it, what actually happens, is manifested due to the confluence of properties of the system and the properties of the context of the system. This is a highly dynamic process. There's emergent feedback between the system and the environment. You might have a context and a proto-system that then manifests a new property, and that property feeds back on the environment itself and changes the environment, which then feeds back on the system again, and you have both synchronic and diachronic components. And this is really important because some of these contexts not only manifest properties, but they screen off elements of the model space from the system in question. So what the system actually does is, in part, not just what it can do, but what it can't do. And what it can't do is defined by the constraints that the context provides on it. Right? Now, I think this kind of floats free of most of what I'm saying, but my particular metaphysical way of describing this is that I like to think of modalities themselves as grounded in a network of property compatibility and incompatibility relations. So the way I think of this is that you have sets of properties that either can be or can't be compatible with each other. And that itself grounds the model space of what can happen or can't happen. Because either those properties can exist at the same time, or can't exist at the same time, or necessitate each other's existence. But it doesn't matter, particularly for the kind of the argument in relation to philosophy of science, whether you think modality itself is fundamental and properties aren't fundamental, or that they're equally fundamental. All that matters is, whatever you're taking to be fundamental as part of the metaphysics, some element comes from the context, not just the system. So, just like there are many ways of describing the world, there are many properties in the world, trivially many properties in the world. Any system we look at has more properties associated with it than a salient to anything that it does. So we privilege certain properties for the nature of explanation and for specifying the precise emergent properties that any system might have. Right? Now, those properties happen to be, I'd argue, the ones that we tend to express using the atomic variables. So even though I cautioned against it, I'm using the epistemology as an argument for the ontology. But it's a funny coincidence, I think, that just the right set of descriptive terms to map the model space seems to pick out properties which, on the face of it, are the properties themselves which are the truth makers for those model spaces. Right? So, in order for this to be an ontological claim about the world, you have to take modal relations ontologically seriously. Right? If you take modal relations ontologically seriously, then anything that screams off or opens up part of this network of modal space that systems actually engage in, that's part of the ontology of the world. Right. So we go back to our kind of honeycomb picture, where you have this web of property incompatibility and compatibility relations that ground the model space. And because the properties aren't all of one level, that's why you have this interconnected picture of the model spaces. The actual model space as a totality is all produced. These separate domains are ways of describing the model space. But in reality, they're all interconnected because the properties of the world all exist at different levels. So, now I'm going to take a slight detour just because I like making controversial claims. So this isn't particularly dependent on the contextual emergence argument I've presented so far, but I think it's an interesting application. So let's imagine that we look at the notion of causality itself and ask, is causality fundamental in the world, or could causality itself, as a property relation, be emergent? So here we've got Kim's causal exclusion argument. The standard way it goes is you have two different levels. So we have some higher level now. In Kim's interests were the relationship between mind and brain. So the higher level would be mental properties, and then the lower level would be the physical properties of a correlate brain. So Kim's argument was this, and it was based on supervenience, the idea that you can't change the top level without also changing the bottom level. So Kim's argument goes like this. We have a causal relation between the higher level properties. M brings about M star. But M supervenes on P. And you can't make a change in M without also changing P. And so you then have this other, and by changing P, that itself causally brings about the state P star, which M star supervenes upon. So for Kim, you have two competing causal stories of the world. You have a top-level causal story, but then through the supervenes relation, you always have a correlate, lower-level causal story. And so Kim's argument is, it's inefficient to allow two causal stories to be part of the ontology of the world. The lower-level causal story is the one that matters. Now, the problem with Kim's argument is that it's too good. So Kim's intention was to show that mental states reduce to brain states. But the problem is, this exactly applies from brain states to cellular states, and from cellular states to chemical states, and from chemical states to kind of physical states, and from physical states all the way down to whatever's at the bottom, if there's anything. Now, one way of viewing this is that it's a reductor, in that you have a causal relation which is overdetermined, so we throw away at the top. But if we go all the way down to fundamental physics, there's a fairly vibrant argument about whether fundamental physics itself has any causation in it all. Some people have a very permissive notion of causation in which everything's causal. Other philosophers are a very tight definition of kind of causality. So, but the point is, it's a very strong argument that is almost too strong to establish just the right amount of reduction that you might want. Kim's completely uninterested in this, as an aside. But how can we get around it? Well, you can't get around talking about causation unless you actually pick a theory of causal explanation, because otherwise you're just talking past each other. There's too many extant accounts of causation to say anything meaningful. So you have to specify one and talk from that perspective. So, I'm a manipulationist, so we're going to use Woodward's manipulationist account of causal explanation. So for those unfamiliar, here's how it works. In Woodward's scheme, manipulations are themselves causal interventions on a physical system that change the state of a variable, an input variable, that then brings about a change in an output variable. And for Woodward, by mapping this territory of input manipulations to output consequences of those manipulations, you map the model structure of the world and provide counterfactual explanations. Now, it's important to note two things. One, it's not a reductive account of causation. Woodward doesn't say what the causal relation is. He uses the causal relation in the definition of an intervention. Right? The second is that not every intervention is causal. Woodward's explicit about this. Woodward's absolutely explicit about this, that some interventions are causal in the sense of they're things that we could imagine doing. Not just a set of things we can actually do, but things that in some ways are well localised in space and time that we could hypothetically imagine doing. But other interventions are things that aren't intelligible in causal terms at all. So, here's an example of Billy breaks a window, and so he does that by throwing a rock, and we have this input variable, Billy throwing the rock, and if it takes one value, then the window breaks, and if it takes another value, then the window doesn't break. Hence, we've established the causal relation between throwing the rock and breaking the window. So, let's take an example from astrophysics, white dwarf stars. So white dwarf stars are stellar remnants that exist after a supernova. So the star blows off its outer shell, and what's left inside is a super dense set of material. The star's no longer generating enough heat to counterbalance its own force of gravity. So the star starts to collapse. As it collapses, it gets denser and denser and denser, until it eventually reaches a point where the electrons have been squeezed together to the point where the Pauli exclusion principle takes up. So the Pauli exclusion principle, based upon the symmetry of wave functions, says that no two fermions can occupy the same quantum state. So even though you squeeze the star together, you can't actually squeeze it together anymore because they can't occupy the state. So it halts the process of collapse. Now, in real astrophysics, if there's enough mass, it can continue collapsing and form a neutron star. And if there's enough mass, it can continue collapsing and form a black hole. But for white dwarfs, if the mass is in the right range, Chandrasekhar showed that it stops at a white dwarf star. Right. So we have this micro-physical explanation of what's happened in terms of the Pauli exclusion principle, which itself, if you look at it more fundamentally, is just an expression of the symmetry properties of wave functions. Now, in Woodwardian terms, I would argue changing the symmetry properties of a wave function is not intelligible as a manipulation. So if we were to think about this micro-physical explanation of what's going on, if I was to say, I'm going to change this wave function from symmetric to anisymmetric, that's not something that I could even hypothetically imagine doing. That's like changing the dimensionality of space or changing a fermion into a boson. It's not something that's continuous with real experimental activity. Right? So that's the micro-physical description. But what happens if we look at the aggregate, macro-bulk description? Well, here, you do a density of states calculation, and you end up with what's called a degeneracy pressure, which is if you actually think about a star, and not just the micro-physical system of particles in a box, you derive this, which is a change of internal energy with respect to volume. Now, this has a whole set of macroscopic bulk variables, which I'd argue are perfectly manipulatable and understandable as causal manipulations. I could add mass to the star, for instance. I could change its volume. Now, what they teach you in astrophysics school is that this isn't a real pressure. So they'll derive this and they'll go, but don't worry about it. This isn't a real pressure. It's not like the pressure in the air and the gas. But of course, then the question is, well, what counts as a real pressure? Because it has all of the bulk properties. It's described in exactly the same terms as the pressure in this room. And actually, this kind of partial differential equation route to deriving pressure is much more fundamental than the just so story that we tell ourselves in first year physics about what pressure actually is. So, I'm arguing that at the macroscopic level, you have an explanation which is interpretable in Woodwardian terms as a causal explanation. And at the microphysical level, you have an explanation, so still a set of what might be described as counter-legal kind of model spaces defined, but they're not interpretable as manipulations. So in Woodwardian scheme, you've somehow gone from having no causation, you have dependency but no causation, to causal dependence. Hence, the causation itself is an emergent contextual property of the aggregate system. If we just had two electrons that we're trying to squeeze together in a box, we'd have nothing more to say about it. But the fact that those electrons are in a star and they're part of an aggregate means that they create a context. The context is the system environment boundary between the star and space. The context is the microphysical context that each electron provides for the other set of electrons. Those allow a set of bulk properties to be defined, to be stable spatiotemporally, to be well defined in terms of manipulations, that allow us to say that the star indeed has a causal explanation for why it ceases to collapse. Right. So, get on to contextual unification. So, I don't know a lot about unification, so feel free to just laugh at me. As far as I understand it, one way of approaching unification is as an explanatory question. So, if we want to compare two explanations of disparate phenomena, we could actually show that we could combine them together and have one unifying explanation which accounts for both things. In unification in scientific practice, it can be extremely heterogeneous. So you can have new descriptive vocabulary that allows two seemingly disparate explanations to actually be both manifestations of a deeper explanation. Or you could have new classificatory schemes where you realise that two things that you thought were different were actually the same. Or new mathematical representations. Another form is what's called physical unification. So you could identify a common set of causes, mechanisms, entities, forces, laws, the list goes on, that these two systems have in common. So if you're Newton and you realise that apples falling to the earth and hitting on your head are the same as planets moving around, then you unify these two systems because they're both exemplars of the same underlying set of structures and mechanisms. So in that sense, unification is almost by definition reductive in that sense, in that it's taking many things and turning them into a subset of those things. It's like you're combining things together to show that something more fundamental accounts for both of them. Right? Two things are both aspects of the one thing. The question is, although it's reductive in that sense, is it reductive in the standard sense that reduction is used in the emergence and ontology argument? So, I would say that unification finds links between disparate phenomena, but it can sometimes do so by moving up a level, not just down a level. So when we think about it reducing, it doesn't imply that the way we unify in the practice of science is by actually just considering what's at the lower level or what's at the fundamental level. Sometimes we unify disparate phenomena by moving up a level and seeing that if we consider higher level properties, two systems are manifestations of the same thing. So we can have radically different microphysical particulars that are accounted for by looking at the same pattern of structural relations. So we could think of critical phenomena in thermodynamics, phase changes, all kinds of things in physics that are unified by thinking of higher level phenomena. In biology, we might think that we've unified the tree of life by thinking of higher level statistical processes in natural selection that can bring about all of the highly disjunctive microphysical states that are the product of evolution. So we haven't unified the tree of life by going down the scale to go, well, are kind of trees and mice made of the same atoms? We've gone up the scale of abstraction to say, are they produced by the same set of structural forces? So my argument is unification can proceed by moving up a scale to find a common pattern in causality or mechanisms, or not just down a scale to find common, more fundamental nomological structure or common entities. Right. So I'd say this makes sense if physical unification is in part about combining sets of model relations of disparate systems to show that each is a proper subset of the larger set of model relations. Or that if we structure that larger set, if we give it a contextual topology, if we write down the relationships that the members of that set have to each other from the one starting set with two different contextual topologies, we could produce the two things that account for the modal relations and properties of two different systems. So, here's another toy example. Let's imagine that our alien friend now wants to unify cricket and baseball. Right? So he looks at, he's an alien, he looks at cricket, he looks at baseball, and he goes, these things seem quite similar. Is there just one description I can give where I can get both of them out? And I'd argue, yes, if he's a contextualist. Because he can show that each one is a particular contextual topology imposed on a common set that they have together. So we can define a set that involves players, gravity, balls, bats, running. But if you impose a particular contextual topology, you can tease out the exact set of properties and modal relations and descriptive atomic vocabulary for cricket as you could do for baseball. But only if you appropriately define the system, context, environment boundary. So, for instance, I have no idea whether this is true or not, but I assume there are different numbers of players in baseball and cricket. So if you have to define who's a player and who's not a player, and if you use the same definition in both games, you won't get the rules of the game right. So you have to know what the difference is between the system and the context in order to be able to specify the atomic variables to account for the modal relations in that system. And by imposing a different system context boundary on the same underlying set, you could produce two radically different accounts of what seem like disparate phenomenon, but actually have a common, unified kind of finer topology. So, we might call a version of this epistemic contextual unification. We unify two descriptions or explanations or theories when we have an algebra observable such that we can recover each description by the set using a different contextual topology. So as I said, we recover each description by taking a different system environment boundary, by using different boundary conditions, stability conditions, but from the same starting algebra. But that's purely an epistemic claim. It's that we can recover this account, this explanation, from both. Now, slightly more radical claim, ontological contextual unification. It's that the property compatibility relations of these two different systems actually ground the model structure. So the physical unification is identifying a common set of structural features in the property compatibility relations between those systems. So we might unify by showing that the properties are actually the same, or by showing that the properties themselves are different, but there's some similar relational structure in how the properties interact with each other. So, for instance, in a case like universality, I don't think the properties are the same, but it's the way the properties are structured together that you could argue is genuinely universal and can be unified into one descriptive scheme. And in this case, one ontological scheme of these higher level structural properties actually driving features of the system. And so it's not just properties, but it's the meta properties, if you want to use that term, of the structure of the properties. Right? So, the different lower level properties combine in a confluence which has structurally isomorphic form across many different systems. And that's what ontological contextual unification would do. So, in summary, contextual features aren't just background conditions. It's tempting to think that because most scientists don't pay any attention to them because they take them as background conditions. It's tempting to think that because most philosophy of science don't think there's anything interesting going on with them. They just say they're background conditions. Of course you have to take some things as brute, some things as background conditions. That's just trivial. Now I'm arguing that if you pay attention to it, it can actually do some philosophical work. The contextual features are important for describing systems, epistemic contextual emergence, and I'd argue they're important for the manifestation of the exact set of model subspace, because it's to do with that exact confluence of environmental and system property compatibility and incompatibility relations that defines that and grounds that modal space. Unification in this scheme isn't inherently reductive in the sense that when you unify two systems, it aligns naturally with the reductionist intuition in the emergence reduction debate. You don't unify automatically by going down to the more fundamental. Unification can occur by considering microphysics, and there are plenty of examples of that. It can also occur by considering high-level structure. And contextual unification can be thought of as specifying a new system context boundary for heterogeneous phenomena to show that they're contextually different manifestations of the same underlying sets of relations, structures, and properties. And that's me done. Thank you very much.